Same compute, lower loss. This is why modern LLMs pick SwiGLU. You're looking at two bar charts showing flops and loss. Notice how the flops are nearly identical between GELU and SwiGLU, but the loss drops significantly with SwiGLU. This isn't just theory. Palm and Llama both standardized on SwiGLU because it delivers better perplexity at roughly the same computational cost. We'll cover this in 3 steps. First, where activations matter in the transformer. Second, what SwiGLU actually does. And third, why the 2/3 width trick keeps compute constant. By the end, you'll see the code and understand the trade-off. Activations leave in the feed-forward network, the FFN block that sits between attention layers. After attention mixes information across tokens, each token passes through this 2-layer network with a nonlinearity in the middle. For years, GELU was the default choice here, a smooth activation that outperformed ReLU in early transformers. But GELU has limits, and that's where gating comes in. Look at the curves for ReLU and GELU. Both are monotone functions. They map each input to a single output with no branching logic. ReLU kills negative values entirely, and GELU smooths that out with a soft saturation in the tails. But neither function can selectively gate features. Every dimension gets transformed the same way, with no mechanism to choose which features to pass through or suppress. The GELU family fixes this by splitting the input into 2 paths, a gate and a value. You project your input vector into 2 separate vectors, apply a sigmoid or similar function to the gate, then multiply element-wise with the value. This gives the network a way to open or close channels for different features. The result is better expressivity. Your FFN can now route information dynamically instead of applying the same smooth curve everywhere. SwiGLU is the specific variant that modern LLMs prefer. The formula is simple. You compute SiLU of x times the first weight matrix, then multiply element-wise with x times the second weight matrix. SiLU, also called Swish, is x times sigmoid of x, a smooth gating function that avoids dead neurons and provides better gradients than ReLU. The gate path uses SiLU, the value path is linear, and you combine them with element-wise multiplication. That's SwiGLU. Here's the clever part. If you naively replace GELU with SwiGLU, you'd add a 3rd projection and roughly increase compute by 50%. But you can shrink the FFN width to compensate. A GELU FFN uses width 4 times the model dimension, requiring 2 projections. SwiGLU uses 3 projections, so you set the width to 8/3 of the model dimension. 3 projections times 8/3 equals 8, which matches the original parameter count and flops. The math works out, same compute, better loss. Why does gating help? Think of each dimension as a feature lane. Without gating, every lane gets transformed by the same curve. With SwiGLU, the gate can open some lanes wide and close others down, letting the network select subfeatures dynamically. SiLU also provides smoother gradients than ReLU, which improves conditioning during training. The result is a more expressive FFN that doesn't cost you extra flops. Palm and Llama both adopted SwiGLU in their FFN layers. Empirical results show perplexity improvements over GELU at matched compute budgets. Llama, for example, uses a model dimension of 4096 and sets the FFN width to 11008, close to the 8/3 ratio after rounding up to a nice number for GPU kernels. The papers cite consistent gains across scales, though the magnitude varies by task. Here's how you implement it. Your module takes the model dimension and computes the GELU width as 8/3 times that dimension. You create one up projection that maps to twice the GELU width, then chunk the result into 2 halves. Apply SiLU to the first half, multiply element-wise with the second half, then project back down to the model dimension. Single up projection, split into gate and value, multiply, and compress. That's the full forward pass. Let's compare GELU and SwiGLU on a toy vector. Same input, same target compute, but the outputs differ because of how features are selected. GELU applies the same smooth curve to every dimension. SwiGLU gates some dimensions more than others, leading to different feature selection. This difference compounds across layers and shows up as better loss curves in practice. Watch out for common mistakes. First, don't use width 4 times the model dimension with SwiGLU. You'll blow your compute budget. Stick to 8/3. Second, apply dropout after the gating multiply, not before, or you'll break the gate signal. Third, initialize the gate bias carefully. If it collapses to 0, you lose the gating benefit entirely. These details matter. SwiGLU isn't a magic bullet. Gate collapse can happen if initialization or learning rate is off. Small models or non-language tasks sometimes see minimal gains. You'll need to tune hyperparameters, especially the learning rate and initialization scale for the gate path. It's not always better, but when it works well.